Dziękuję bardzo. Ja oczywiście czuję się szalenie zaszczycona tym zaproszeniem na zjazd fizyków polskich. Przypomniałam sobie, że ostatni raz miałam okazję występować tutaj prawie ćwierć wieku temu. Ci, którzy mnie znają, wiedzą, że jestem uczennicą profesora Wróblewskiego, ale nie odziedziczyłam po nich zdolności do pamiętania dat, także dokładnej daty nie pamiętam. Jak również wiecie wszyscy, że profesor Wróblewski ma straszny rygor językowy, w związku z tym ja nie miałam odwagi cywilnej, żeby mieć wykład po polsku i od tego momentu przejdę na język angielski. This is basically the overview of my talk. So first of all, I would like to justify the content of my talk. And so I will say a few words about the role of CERN and the European Committee for Future Accelerators, of which I am a chair right now for another half a year. I will have a very short overview of the status of the standard model of particle physics. We heard a presentation already in the previous talk. The question, what is missing, and therefore, what are our future prospects? So the time distribution among those points is very non-equal. So let me start by CERN. So the discussions about CERN started sometimes in 1949, and the name is derived from French. In English, it's European Council for Nuclear Research. The provisional body was founded in 1952, but officially CERN was initiated in 1954. And at that time, there were 12 European member states, signatories of the mandate of CERN. Today, there are already 22 EU member states and 7 associated member states. And among the associate member states, there is India and Pakistan, so also the geographical reach of CERN is increasing. Now, an interesting and also personal point is that I was still employed by the University of Warsaw when Poland joined CERN as a member state in 1991. Turns out this was the year where Israel, where I reside today, became a member, an observer state, and Israel became the 21st member state in January 2014. So personally, I joined CERN twice in my lifetime. So CERN has a huge accelerator complex, the largest of which is the LHC, the largest circle that you see. It delivers antiprotons, neutrons, many other beams. For example, here was the famous neutrino beam with results which were not confirmed later on. Now it is being used for new accelerator technologies. So it's a very rich laboratory in terms of infrastructure and diversity. But definitely the present energy frontier is reached at the Large Hadron Collider at CERN. So this is built inside the 27-kilometer tunnel, which was originally for an E+, E- collider, LEP. It goes sort of 175 meters deep in certain places. It's populated by more than 1,200 superconducting bending magnets. I'm just trying to give you, the size of the project. Each of them is about 14 meters long, and the magnetic field, the bending magnetic field, is 8 Tesla. So till now, data were collected at 7 TeV of center of mass, then at 8 TeV. 8 TeV, this is which allowed the Higgs boson to be discovered. And now we are taking data at 13 TeV, which is almost the nominal energy, which was supposed to be 14 TeV. Now, the history of ECFA is quite interesting because ECFA was called initiated by Viktor Weisskopf when he was the Director General of CERN in 1963, because he realized that many of the European nations had their own ambitions of developing national labs, and it became extremely important to make sure that there is no competition. On the contrary, there is complementarity, and therefore he wanted to have a body which would represent the European community, at the same time making sure that basically the potential of Europe would be used to its fullest. Till today, ECFA is an advisory body to the CERN management, the CERN Council, because the CERN Council is the one which has the money, and therefore the decisions are taken at the level of the CERN Council about the future of the CERN facilities. There are various committees and other national and international organizations. The guidelines of ECFA were worked out in many steps. Lately, we will have also to extend its mandate to define the membership of ECFA because of this geographical enlargement of CERN. And basically, its mission is to the long-range planning of high-energy facilities. This was the original one, which includes accelerators, large-scale facilities. They should be matched to resources and size of communities. The idea is also to make sure that there is equilibrium between the role of national and international laboratories and institutions, in particular universities. There is a close relation between research and education. We are very much sensitive to outreach. And then we are also checking whether there are adequate conditions within the various member state countries. That means a lot of traveling, and I have to say that for the last 2.5 years I had at least one trip per month, so I became more of a travel agent than physicist. We organize regular meetings in which we're trying to have reports on the activities going on in the community. This is called the plenary ECFA. We have also restricted meetings where we discuss the progress happening in various countries. We do visit the European countries on a regular basis. There are also ad hoc symposia, workshops, depending on the projects which are being discussed. We also follow up the regular demographic studies of what's happening in the European countries, etc., etc. And then I have to report once a year to the CERN Council about the activities of ECFA. So this is basically the background of what I will be discussing slowly. I will start discussing now. So the status of the standard model, I think it's common knowledge right now that we basically covered all the building blocks of matter. We also have covered all the interactions, weak, electromagnetic, and strong. About the gravitational issues you already heard. I'm not touching that subject. And we do know a lot about the various components of the standard model. The Higgs sector is very new. It's only about 5 years. This is not really enough to understand all the details. And also the top sector is largely unexplored, mainly because after its discovery in Fermilab, it was not really very copiously produced, while at the LHC, it's really very, very copiously produced. So we're still working on closing some of the issues in the standard model, and of course hoping that maybe we will see some deviations from the standard model. So this is, I don't want you to look into details in this, on this plot. This is basically a summary of all this production cross-sections that have been measured at the LHC. The important issue is that in terms of size, they cover sort of 15 orders of magnitude. And if you look at the ratio between the expectations of the standard model and the measurements, basically there is a perfect agreement, very much along, ratio equal to 1. There are, funny things happening at the end where the cross sections are very small, but it might be just an issue of statistics. So no claims here. We just have to work harder. Of course, there is quite a large community, and more than half of the papers coming from the Large Hadron Collider community concerns basically searches for deviations from the standard model. We don't seem to observe anything, and those are the various limits that people achieve. So basically, we are up now to about 3 TeV, and we still don't see any new objects in this range, but we don't lose hope. There is still more luminosity to come, and probably more energy. So what are our guidelines from the LHC results? So first of all, I think the standard model is doing really amazingly well. The Higgs scalar is very much like expected in the standard model, but still the precision with which we make the statement is not particularly impressive. There is no indication of physics beyond the standard model in terms of discoveries, up to scales of the order of 1 to 3 TeV. Now I should mention, and this is going to be covered in the next talk by Andrzej Buras, that there are some hints appearing in the sector of lepton flavor, lepton number and flavor number conservation from the LHCb experiment, one experiment which is totally dedicated to basically the study of beauty and charm decays. But I'm sure that Andrzej will cover that. What are the guidelines from outside LHC? Well, we know that neutrinos have masses because they oscillate, but we don't know of any mechanism in the standard model that would generate these masses. We know that there is dark matter in the universe, and we don't have a candidate for that in the standard model. We know that there is a prevalence of matter over antimatter, and we still don't have an explanation for it. And then there are theoretical arguments that theory is not really complete, and this is somehow shown by these images produced by Matt Strassler, which I like very much. Basically, we're talking about a theory being natural. So imagine that you have a big party with small kids playing around the table on which you have a vase of flowers. And of course, they move the table. So if you see after the party that the vase is still on the table, it's natural. If it's on the floor, it's natural. But the last thing that you expect is that the vase is basically hanging on the edge of the table in a stable way. So apparently, this is what the standard model is about. This is a vase standing on an edge. And we have to understand why it's not falling. The next question is then, how should we go about trying to understand all these issues? And of course, we're talking about accelerators and experiments at accelerators. That's what I'm representing. Then we would like to be able to make control experiments at accelerators. And right now, conceptually, and this is going to be a very interesting period in our lives, we are thinking about energy frontier, making accelerators with higher and higher center of mass energy, and that we know how to do with protons because they live very long, so we can treat them for a long time. The other option is precision frontier, so that we know how to do with electrons and positron beams. And then there is something in between, which is a density and scaling frontier, and this is electron-proton scattering. And inside all these circles, you have the various projects that are being discussed. And I'm not going to go into the details, but I'll tell you a little bit more what would they mean. And we will have to make soon a decision, a prioritization of this project. So just so that you know what I'm talking about in terms of dimensions, I like very much this plot. Don't look too much to the left and to the right to the numbers, but basically in the size of accelerators, the circle inside is basically the LHC, okay? And all the new projects that we are considering are accordingly much, much higher. The largest right now is 100 kilometers. That would be about 4 times longer than the tunnel of the LHC. And then we also think about linear colliders, because electrons don't like very much to go into circles. They tend to lose a lot of energy by synchrotron radiation, so it's much more efficient to produce linear accelerators, and the size of those would be of the order of up to 50 kilometers. So we start discussing very large sizes, which carry, of course, their own price tags. That's why we have to think very hard which way we would like to go next. So for the energy frontier, proton-proton colliders, what is being discussed right now is to upgrade the magnets which are inside the LHC tunnel through high-temperature superconductors to maybe 16 Tesla and maybe even up to 20 Tesla. So this is now being worked on. It's very difficult because these high-temperature superconductors are usually very brittle, so it's very difficult to make a coil. It's fascinating to see how this is being developed and the design of the magnet. If that works out, then we could double the energy which is in the LHC. We would be able to go to 28 TeV and even to 32 TeV center of mass if we reach 20 Tesla. Then there is this whole new project, a project of the future. Here you see where it would be built. It would be built under Geneva, under the lake of Geneva and around the Salève. And this would be, compared to LHC, a 100-kilometer tunnel. Again, depending on the magnet, 16 to 20 Tesla, we would be able to reach something like 80 to 100 TeV proton-proton interactions. Now, China is basically following most of these developments and these ideas because in principle they would have the funds to build it all by themselves. So they are also thinking about a proton-proton collider anywhere between 35 TeV to 65 TeV, and maybe even a larger tunnel of 100 kilometers, in which case they would also reach almost 100 TeV. They're working in slightly different high-temperature superconductors based on iron. So this is geographically, it's somewhere south of Beijing. Somewhere around here is the city where I was born, Tianjin. So we are in the north of China. But the problem with the energy frontiers with proton-proton is that proton-proton interactions are extremely complicated, and this is what you're supposed to see here. So basically, there are, each proton is consisting of partons, quarks, and gluons, and so we have basically two wideband beams that collide, and then there are many things happening. It's not always very efficient in terms of trying to get all the energy available in the center of mass towards one interaction. And therefore, here this is basically a very interesting plot which tells you that if the limit, for example, when we were running at 8 TeV center of mass, and we collected, this was in 1 year, 10-20 inverse femtobarns for the measurements of the cross-section. So if we were able to reach a limit of 2 TeV, meaning that if there were objects lighter than 2 TeV, we would have seen them, then to reach 5 TeV, we have to go to 14 TeV center of mass, so we almost double the center of mass energy, and we have to go almost a factor 15 in terms of collected statistics. So that means basically running 10 years longer. So as you see, the proton-proton machines are not very efficient, although this is the only way we know how to reach really a very high energy. They have also the other problem is that the calculation in quantum chromodynamics are very, very difficult, and they take a lot of time. So this is now on paper. This is not, construction. And this was a beautiful example presented by a theorist, which said that, showed that while we observe about, let's say, effectively 2 million Higgses at the LHC, in terms of 1977 numbers, we should have expected only 1/4 of it. Already by 1990 we were expecting sort of 20% less. Even next to leading order calculation in 2010 didn't give us a perfect agreement. You might remember that, we started with 30% higher cross-section, which was very lucky because this way we were able to see the Higgs. But in fact, after calculating another 70 million graphs, there is a perfect agreement. So what I'm trying to say is that, we work very hard, we try to make very hard measurements, but they also require a lot of attention from the theory side. So the other option maybe is the precision frontier. So the precision frontier, but at the same time at high energy, would be electron-positron colliders, because there the theory, the calculations are much simpler. And one of the examples was that, for example, at LEP, one could already see the presence through higher order corrections. One could see the presence of the top quark. One could, in fact, predict the mass of the quark top, although it could not be yet produced on shell. We could not see it in the detector yet, but it was already affecting the interaction. So the hope is that by making this very precise measurement of the standard model, we would see departures and then be able somehow to figure out at what scale they are happening, and maybe then the design of a proton-proton collider would lead us towards, learning more. So this is another, this is from the experimental point of view, a way of seeing the big difference between what's happening in the proton-proton collider and in a electron-positron collider. So this is how the Higgs appears in the gamma-gamma channel, not the cleanest, but the optimal channel to look for the Higgs production at the LHC. As you see, it's sitting on top of a very large background. So basically we have more, oops, it's very sensitive. We have much more background that we have Higgses, while by making sort of a missing mass experiment at the E plus E minus collider, we have a beautiful peak and with the full shape of the mass of the Higgs. Also, as in terms of the precision that can be achieved because of the experimental conditions at an E plus E minus collider, you're supposed to look, the red lines, the red, give you the idea what is the precision in about the same time frame that one can reach on learning how the Higgs couples to matter, as opposed to the Large Hadron Collider, which is this dark green. So there is only one channel in which the Large Hadron Collider is much better than the E plus E minus collider. So energy frontier, precision frontier. So in the precision frontier, there are also many candidates. Right now, the International Linear Collider has been invited by the physics community of Japan. It would be built in Kitakami, which is a little bit north of Sendai. We still don't have a decision of the Japanese government, so it's still only a project on paper. This is the most advanced project in terms of the technical design, meaning, in principle, this is what we are told, the day there will be financing, it can start to be built. So right now, in order to try to cut down on the costs of this project, we are talking about a baseline of 250 GeV. Remember, the mass of the Higgs is 125 GeV, so this would be a Higgs factory. We wouldn't be able, for example, to produce the top and anti-top quark, so we would have to concentrate on the Higgs sector of the Standard Model. Then there is this compact linear collider which CERN has been designing with a new technology where the power of the RF cavities is driven by another accelerator beam. So it's a little bit shorter and cheaper. The level of acceleration is also a little bit better. So the baseline here, optimal, would have been 280 GeV. It could be extended with time, so one would start with an 11-kilometer linear tunnel and then extend it up to 50 kilometers, unless with time there would be new technologies coming in with a much better acceleration elements, in which case, the tunnel could have been shorter, and this is the way to think about it. So we start smaller. The advantage of CLIQ would be, of course, that we are then above the top production threshold, so we have a little bit more physics to investigate. Now, people at CERN are also fascinated by the idea of starting this 100 TeV tunnel for the large proton-proton collider by putting sort of almost standard elements, by now accelerating elements, to make an E plus E minus collider first. They could reach any energies of the order of 200 to 350 GeV. It's not yet clear what the synchroton radiation would do to that, but it's one of the issues which is being considered. And then China is basically also thinking about, if they were to go for this large proton-proton collider that I mentioned previously, they would also start from an E plus E minus collider. Now, one thing is basically clear from all of us, that we won't have two large colliders. There will be one. So that's an interesting discussion. Is it going to happen in China, in Europe, or anywhere else? Now, there was also an interesting paper that I encountered, and you will see all the references at the end of my talk. In principle, there is still this tunnel which has been dug in Texas in the 90s to produce a proton-proton collider, and then at 25 TeV. It has 87 kilometers length. It has been filled up, but apparently it's easy to clear it up. And it could be resurrected to build a circular Higgs factory. So there are many options. So this is the geographical location of basically the CLIQ. So CLIQ, so this is, you see the LHC. So the tunnel of CLIQ would be not much, it would cross, originally it would cross the LHC. And would be, for 380 GeV, we would have about 11 kilometers tunnel, which is not too much. While the FCC tunnel would be much, much bigger than the LHC. Now, there is another precision frontier that we could reach with a muon collider. This is actually extremely attractive because there the sizes are much, much smaller. In principle, 120 GeV could be achieved at 300 meters, so it's almost nothing for a particle physicist, and it could be extended to 5 TeV because the muons don't radiate that much. However, they don't live very long, so we still have a big challenge how to collect enough muons to actually make a beam from which we could see interactions. The other issue with the precision frontier is that somehow the circular colliders seem to be able to achieve a much higher luminosity. So this is the luminosity as a function of the center of mass energy of a E plus E minus collider. So the luminosities can be order of magnitudes higher. However, they cannot, because of synchrotron radiation, they cannot go really below above 300 GeV center of mass, while all the linear colliders can be simply, extended with time and with money. So that's something that will have to be discussed also in our future plans. Now, I wouldn't be myself, and if I didn't talk a little bit about the proton structure and QCD, because this is my area of expertise and what I like. And I just wanted to show, don't go into the details of all the bubbles and things, but this is what it takes to get the standard model predictions for the Large Hadron Collider. So it keeps many theorists and experimentalists very busy. But one of the issues which is very important is to have the parton distributions in the proton. I remember I told you that, in fact, when two protons collide, there are two wide beams of partons colliding. And if you want to know the energy distribution, we have to know what is the energy distribution of these partons inside the proton. Well, it turns out it's actually more complicated than that, because also they have a spatial distribution, and we have many reasons to believe that basically the proton is much more complicated than what we tend to think it is. And you have to remember, and this is very important, that we are all fascinated by the Higgs. Of course, it's a new discovery, but the mass of the proton is only in 5% generated by the Higgs. 95% of the mass of the proton, unfortunately, is generated by quantum chromodynamics. And we do not really understand, because this is related to confinement, we don't understand exactly the mechanism. And so there are many of us on the side of particle physics and nuclear physics that are trying to figure out how is this working. And it is an important input for all the future Large Hadron Colliders. So there are also projects of trying to explore the proton in more details. And the more realistic right now is, I don't want to spend too much time on these plots, is basically a project which is now in the States, discussed in the States. I think it has a very good chance of success. It's called the electron-ion collider. There are two possible locations, either at Brookhaven, where there is already a proton circular accelerator, or at Jefferson Lab in Virginia, where there is already an electron collider. So now there will be an interesting discussion where the project should go, should it be funded, and what is the situation in the States right now. Also, some of the aficionados of QCD would like to see at some point a beam shot into the LHC, the protons of LHC, to do the electron-proton collider there. And of course, for the FCC, the same thing. So I'm going to skip this one. It tells you what would be the roadmap for this electron-proton colliders. I should also mention the new accelerator techniques. It's a fascinating area. Not that I understand all of its elements, but this is basically plasma wake field acceleration. And there is now one very interesting project going on at CERN, whereby the idea is to take a proton beam to transfer the energy through plasma to a beam of electrons, in which case one achieves typically accelerations of the order of 100 gigawatts per meter, which is instead of the 100 megawatts that we're talking about for click. So this would be a tremendous change in the whole technology of accelerators. We would be talking about little ones like this, for daily use, and then slightly bigger ones for research. So the proof of principle is underway now at the SPS at CERN. So this is something to definitely follow up. Now, the time scales, this is another important issue. So one thing that the director of accelerators at CERN tells us, that it takes about 20 years from conception to the beginning of building a project, simply because there are so many technologies that have to be developed. So this is the map. This is our future. And so the size of the distance between two curves gives you what is the time uncertainty that is related to it, while this is the time frame. So how are we going to go about it? I have to start finishing soon. So we have a process which is called the European strategy, which in 2013 decided that LHC is going to be the main focus of research in Europe, and then that people should be working on the plus and minus collider. There was also the issue of supporting neutrino physics, where in the States and in Japan. It's all working very well. And time has come now to update this strategy, and basically the process will start in 2019. The hope is that it will converge sometimes in spring to 2020. It means that by 2020 we should know where is our future, and we will see. That's going to be very interesting as a discussion. So let me go to the outlook. The community is very busy thinking about the future, driven by the physics case, of course. There are many exciting developments. The time of the various projects is very uncertain. There are technology issues, funding issues. Right now, what we know is that the high luminosity LHC has been approved, so we will be busy till 2037. For the near future, it looks like the electron-ion collider in the States is the most realistic one. And so I'm expecting very heated debates in the next European strategy update. Thank you very much.
Dziękuję bardzo za bardzo interesujący wykład. Być może mamy z 1 minutę na jedno krótkie pytanie. So as any short questions.
Pytania mogą być po polsku.
Pytania mogą być po polsku. Nie widzę, więc jeszcze raz dziękuję bardzo.
Dziękuję bardzo.